Have you ever just felt that biology is, well, messier than other sciences? Less about these beautiful, clean laws and more about just memorizing this endless, complicated pile of details? If you have, you are definitely not alone. Today, we're going to dig into why biology isn't just different. It might actually be the hardest science of them all. Let's dive in.
All right, here's our game plan. We'll kick things off by setting up biology against the simple elegance of physics. Then, we're going to hit the core idea of this whole explainer, what we're calling life's low compression ratio. We'll see how that plays out in a real-world disease, and then wrap it all up with why this complexity is so important for the future of science.
So right out of the gate, is biology really the hardest science? Now let's be super clear. We're not saying it's less rigorous than physics or chemistry. Not at all. The real challenge, the thing that makes it so tough, is something totally different. It's baked right into its fundamental nature. I mean, just think back to high school or college, right? Didn't it always feel like for every single rule your professor gave you in biology, there were like 10 exceptions you also had to memorize? It's such a common feeling. You learn some big principle, and then immediately you learn about all the very specific situations where, well, it doesn't quite work that way. So why is that?
Okay, this slide right here gets to the absolute heart of it. On the left, you've got physics. One beautiful, simple law. F equals ma. It works for a planet, it works for a pendulum, it just works. Then you look to the right. That whole tangled mess, that's just a standard diagram for one single signaling pathway in a cell. It's this massive web of interactions and feedback loops, and it just screams how different the basic rules of the game are here.
To really wrap our heads around why biology looks so incredibly different, it actually helps to look at the scientific ideal that physics represents so perfectly. This constant search for a simple, elegant, universal explanation.
You see, the classic goal in physics, something that thinkers like Richard Feynman talked about all the time, is to find these really compact but incredibly powerful laws. The whole idea is you can take this huge, overwhelming amount of data about the universe and just boil it all down to a tiny set of principles that can predict what's going to happen next. And this approach has been unbelievably successful, right? It's kind of shaped our whole idea of what a good scientific explanation should even look like.
Okay, so if physics is all about finding those small, elegant laws, then biology seems to be defined by how much it resists that exact process. And this brings us to the central idea for today, the concept of a compression ratio. Just think about zipping a file on your computer. A high compression ratio, that means you can take a gigantic file and shrink it down to something teeny tiny without losing any of the important stuff. But a low compression ratio means that if you try to shrink that file down too much, you start losing critical information, and the file basically becomes useless. While science kind of works the same way.
And this is exactly what we see in physics. It has a super high compression ratio. You can take countless observations about gravity and motion and compress them all into one neat little equation. It explains falling apples and orbiting planets. You've essentially compressed this vast amount of reality into a very small and very, very useful package.
But you just can't do that with biology. If you try to create one simple universal equation for, say, metabolic disease, you'd have to strip away all the context, the specific type of cell, the organism's history, its environment. And in biology, that context isn't just background noise, it's everything. It's where all the meaning is. You lose the context, you've lost the entire story.
So, okay, why can't biology be zipped up like this? Well, it really boils down to a few key things. It operates on a bunch of different scales all at the same time. Its present is always shaped by its past, it's constantly adapting and changing, and it's just full of randomness and backup systems. Let's unpack that really quick.
First up, biology is deeply multi-scale. It's like this stack of interacting systems. You have molecules making up cells, cells forming tissues, and on and on. But here's the kicker. At each new level, totally new properties emerge that you never could have predicted just by looking at the parts below. The way an organ works isn't just the sum of its cells, it's about the complex network they create together.
Second, history matters. Oh boy, does it matter. Biology is what you'd call path-dependent. What an organism can do today is totally constrained by its evolutionary past. It could be a massive event like the rise of oxygen that forever changed life on Earth, or a lab experiment where E. coli needed thousands of generations of setup mutations before it could finally evolve a new trait. Or even how a fish repurposes an old gene to make antifreeze for its blood. The past is always dictating what's possible now.
And if that wasn't enough, biology is also super noisy and redundant.
You can have two genetically identical cells sitting right next to each other in the same dish, and they can behave differently just because of random chance. Plus, biological systems are packed with backup plans. You can knock out one gene, and often nothing happens because another one just steps up to do the job. That's fantastic for survival, but it's a nightmare for scientists looking for a simple cause and a simple effect.
Okay, I know this all might be sounding a little abstract, so let's make it real. We're going to look at a single, very familiar disease, type 2 diabetes, and see how all this complexity plays out in the real world.
A disease like type 2 diabetes isn't about one single broken part, what a scientist might call a single lesion. Nope. Instead, it's a system failure. It's what happens when this whole giant network of interconnected systems all across your body starts to go haywire.
In fact, clinicians now have a name for this, the ominous octet. Just look at this list. There are at least 8 different organ systems involved. It's not just the pancreas. It's the liver, it's your muscles, it's your fat cells, your brain, your kidneys. The list just keeps going. Every single one is playing a part. And right away, you can see why a drug that targets only one of these is going to have a tough time. The real problem is the network itself.
And believe it or not, it gets even more complex. The causes of the problem exist across all those different scales we talked about. You've got issues with molecular signaling inside the cells, stress at the cellular level, inflammation in the tissues, bad communication between organs, and of course, all of this is tangled up with our own behavior and environment. They all just feed into each other. So what's the big picture here? What does this all mean? Recognizing this deep, unzippable complexity isn't just some fun academic exercise. It has huge, real-world consequences for how we actually do science and how we treat disease.
So in the real world, what does this mean? Well, for one, our research has to be designed to embrace all this messiness, using new tools that can see the variability that our old methods would just average away. We can't rely on just one kind of scientific model anymore. We need a whole toolkit. It also helps explain why studies are so hard to reproduce sometimes. It might not be bad science, but a biological context that has genuinely changed. And finally, we have to teach biology not as a list of facts to memorize, but as a way of thinking about these incredibly complex, interconnected systems.
This quote here just nails the takeaway. The point is not that everything causes diabetes. That's useless. The real, difficult work is to trace the actual causal pathways as they snake through all these multiple interacting layers. And this leads to a pretty fundamental shift in how we think. For so many challenges in biology, we aren't really looking for a single silver bullet solution. What we're actually doing is learning how to manage the complexity of a living, breathing, adapting system.
So I'll leave you with this question to chew on. If life doesn't have those simple, universal laws like physics, then how should we even be searching for answers? It suggests we need brand new tools, totally new ways of thinking, and just a deep appreciation for the context, the history, and the beautiful, messy, irreducible complexity of life itself. Thanks so much for tuning in.